Welcome to the Chapter 13 lecture for the Management 3120 Operations Management course. I am Dr. Bill Perkins, and I'm going to provide you a video lecture based on the material found in the textbook Practical Operations Management, 2nd edition, from Natalie Simpson and Philip Hancock. Our objectives for this chapter is to define quality through variation and understand how to diagnose assignable variation and understanding the importance of drafting control charts. So let's get started. Even seemingly identical objects possess small differences. For example, the contents of two bottles of the same beverage, when measured closely, could be expected to vary a small amount. Just as the width or alignment of the bottle labels might also vary slightly. Now, for this reason, successful organizations monitor the quality of conformance or the degree to which a good or a service meets their expectations, or to ensure their customers' ultimate satisfaction. So, for definition purposes, quality of conformance is the degree to which the output of an operation meets the producer's expectations. Now, when considering defects, which for definition purposes is a single identifiable deviation from acceptable conformance, think of the manufacturing of a board game or a puzzle, whereas they both have many pieces that contribute to the overall functionality of that game or puzzle. Any deviation or failure to include a piece would interfere with that functionality. So therefore, it would be paramount to engage in quality control efforts to ensure there is conformance to the design specifications. Now, natural variation, sometimes it's considered a random variation in a process, is a variability that cannot be avoided. So in the previous slide, we referenced a board game or puzzles, the random differences in the thickness of the pieces, which would affect the functionality, is a random or natural variation. Could be the raw materials, maybe have a thickness in certain areas of the actual material that's unavoidable. Cardboard when cut sometimes, like if you think about a puzzle made of cardboard, may have areas where it's more thicker than others. Now, since natural variation represents some randomness that is always present in production, it should be relatively easy to observe, document, and describe. Now, generally, that randomness occurs within a process or between samples. Non-natural variation in a process is called assignable variation. That's named after the fact that this type of variation can be assigned to a specific cause. Now, the distinction is important for two reasons. The first being that this type of variation creates defects or unacceptable units of product. Now, once created, defects must be located and destroyed or repaired. Otherwise, these defective products will be likely be returned by or recalled from those customers unlucky enough to receive them. Now, all these activities represent additional costs to the operation, including the loss of the customer's good opinion of a product. I'm just going to cover a little bit more about assignable variation. So assignable variation is also significant because it has a source, implying that if it is assignable variation, or let's say it's detected, it can be traced to and fixed at its source, otherwise called a root cause analysis. In other words, assignable variation is a signal that a problem is emerging somewhere within the system, that manufacturing system. Or it could be anywhere in the production system, which serves as an invitation to stop the normal production and locate and resolve the problem before it grows worse. So you think about the differences between natural and assignable variation. Think about eggs, okay? Size and weight will vary to a certain degree. and at times maybe even a deformity will make it through the process, all exhibiting the signs of natural variation. Then you think about the times where you open up an egg carton and you see a cracked egg as a result of shipment infractions or mishandling at the food store, or issues that result in a deviation from incubation, or sanitizing processes. You hear of people getting sick because the eggshells weren't sanitized properly, or even in incubation. Sometimes you crack an egg, and let's just say the yolk looks a little discolored. That could at times be as a result of natural, or it could be from the assignable variations, depending on what the contributing or the root cause was. But these are just some examples of natural versus assignable variation. Now, much of quality control is formally known as statistical process control, or SPC. It's a set of concepts, tools, and procedures that monitor active processes by sampling output. So if this sampling suggests that only natural variation is present in the output, the process is said to be in control. So, however, if the sampling indicates that the presence of assignable variation is present, the process is then declared out of control, and the decision to stop production and search for its root cause usually follows. And sampling is a concept critical to the statistical process control, outlining the natural behavior of samples. Control charts are graphs that are actively updated by plotting the values of samples taken at regular intervals during operation. Now, during process operations, each member of the sample is measured for a particular specification, and the chart is designed to monitor these the samples. And these measurements are then summarized as a single sample value, such as the sample's mean measurement, and is plotted on the chart. So if a sample falls outside the acceptable limits when plotted on the chart, this is interpreted as a signal that assignable variation is now present in the process, and as such, the process is declared out of control and should be stopped as far as production goes. So control limit is a control chart boundary where values observed beyond this limit signal the process is not in control. And because this sampling distribution, when everything is running smooth, deviation from the mean is usually non-existent. In reality, a small but ever-present chance exists that the process could create an unusually small or large sample observation while in control. So since the upper and the lower limits must be set at some certain finite value, these limits exclude at least a small part of the natural distribution where this unusual natural sample would fall outside these limits. And then this would signal that the process is therefore out of control, when in fact it may not be. Okay, it may just be random, and the process may not be out of control. And this is known as a type 1 error, concluding that the process is out of control when it is in fact not. And the danger of this happening is known as the producer's risk, because of the likelihood that the production will be stopped because of this identification or this root cause analysis needs to ensue upon seeing this signal, but the producer will be unable to find any assignable root cause because it really isn't a problem. Now, widening the span of the control limits decreases the risk of a type 1 error, but will introduce or increase another risk known as a type 2 error. And a possibility exists that assignable variation might corrupt the process, but the particular sample taken during the time nonetheless falls inside the control limits, sending a false signal of control. So wider control limits, which reduce producers' risk, also allow more variation of any type to fall within the limits. Now, this danger of undetected assignable variation is the consumer's risk, implying that defects are escaping detection and will be passed along to the customer. So for definition purposes, a type 2 error in quality control is concluding the process and is in control when it is in fact not. And consumer's risk is the likelihood of a type 2 error. Now, designing a good control chart is primarily an issue of locating its limits. So setting these limits is particularly, partially an issue of balancing the producer's and the customer or consumer's risk. Now, however, no successful balance will be found if the process itself is not capable of supporting production. So the issue of whether the process is appropriate given the requirements of the design is known as process capability. And that is the natural variation in an existing process stated relative to the allowable variation specified in a product's design. Now, perceiving quality as an issue of conformance to standards dates back to ancient craft guilds. This outlook developed further during the Industrial Revolution in the 18th century, but many of the current methods to measure quality emerged with the concept of scientific management and methodology, stressing the use of data collection and analysis to redesign the processes and improve efficiency. Now, the traditional quality management system encompasses inputs, transformations, then outputs. So for inputs, quality management efforts would entail inspecting arriving products for conformance using acceptance sampling methods. And then for transformations, quality management efforts would entail inspecting work in process for conformance using control charts as a quality method. And finally, for outputs, quality management efforts would entail inspecting finished outputs for conformance using acceptance sampling as the quality method. And the oldest understanding of the concept of quality is the degree to which a product conforms to the producer's standards. Traditionally, quality management supports the vision, employing tools such as control charts to monitor for conformance at all stages of production. Ironically, focus on conformance is also an excellent example of outcome bias and the sometimes mistaken assumption that a good outcome automatically indicates a good system. A traditional view of quality focuses on conformance to specifications, so implementation relies heavily on sampling and inspection. Since inspection is the cornerstone of this style of quality management, such a program often employs full-time inspectors. Thus, employees conducting quality inspections are not the same employees creating the product and may even be organized into a quality control department wholly separate from production personnel in a functional organizational structure, which is an organization of specialists grouped into distinct departments. Now, while this separation of production and inspection is not strictly harmful, it is generally the trademark of an older quality management system and often deliberately avoided by more modern programs. And a traditional approach to quality is also founded on the idea that an ideal amount of inspections exists, some optimal amount of inspections that those full-time inspectors should be providing. Now, the traditional mindset is neither correct or obsolete, but is usually considered incomplete for managing quality in modern times. Relying solely on statistical process control to maintain quality will leave a business vulnerable in the long run due to its focus on shorter-term tactical issues and its assumptions concerning the cost of nonconformance. An inspection-intensive program also brings up the issue of tolerance or setting the boundaries on permissible variation. Tolerances are at least particularly determined by the cost of nonconformance, which is traditionally assumed a linear function of the degree of nonconformance. So, for example, if the difference between an actual measurement and its specification were found to be twice as large for one unit of product versus the next unit, it would be assumed that the previous unit would cost the organization twice as much as the next unit due to its nonconformance. Now, in the 1970s, Taguchi introduced the idea that this linear assumption may be, in fact, a very poor explanation of the true cost of quality. Rather, the true combined cost of nonconformance is more likely to rise sharply with the degree of nonconformance is more likely to emerge as a non-linear fashion, or in a non-linear fashion. So this model is not described as is now described as the Taguchi loss function, and it's illustrated here on this slide. Now, because the Taguchi loss function suggests that all but the smallest deviations from the target are likely to result in unacceptable loss, it further suggests that tolerances should be set much tighter than assumed necessary by the traditional perspective. Now, even if an organization is producing products that minimize the Taguchi loss function through tight adherence to specifications, this does not guarantee that the organization is producing value. Perhaps the greatest vulnerability of focusing exclusively on conformance concerns the origins of the specifications defining that conformance. So while specifications represent the producer's expectations of the product, this does not necessarily mean that the product will meet the customer's expectations. Now, bridging this potential gap between the producers and the consumers' views of product quality serves as one of the essential pillars of many modern quality programs, but even these programs rely on statistical process control in the implementation of product designs. So as a result, tools such as control charts and acceptance sampling remain critical components in the operations of many complex production systems. So on one level, designing a control chart to monitor a process helps to determine appropriate values for control limits. However, the method used to set these limits must be appropriate for that particular situation. Now, correctly determining the limits on a control chart depends on the following three factors. The issue being monitored, the quality of information about that natural variation in the process, and the degree of producer's risk deemed acceptable. So a mean chart is a control chart used in monitoring the key essential tendency of some characteristic within a sample, also known as an X-bar chart, in referencing to the plotting of the averages. And if you are monitoring the proportion of something in a sample instead of an average measurement, a P-chart, which is a control chart used in monitoring the proportion of some characteristic within a sample, may be your best option. And if there is no fixed sample size, a C-chart, which is a control chart used in monitoring the count of some characteristic within a sample, may be your best option. Now, control charts monitor transformation processes as they operate. So similar to the setting for control charts, inputs and outputs are not likely to be inspected completely, but rather sampled for conformance. Unlike control charts, the decision in this setting is not whether to stop production, but whether to declare a larger batch of input and output as acceptable based on the smaller sample. Thus, this process is known as acceptable sampling, and this crucial acceptance or rejection decision is made according to a sampling plan developed for that operation. Now again, a sampling plan is a defined procedure for conducting acceptance sampling, including a criteria that determines rejection of that batch being sampled. Sampling plans are based on the following criteria: the size of the samples, the size of the lots or batches being sampled, the number of samples to be taken. For example, a large batch might be judged on one sample, but should a sample fail to pass some test, a second sample is taken. And the rule for acceptance versus the rule for rejection. And for example, if no more than a certain number of defects are found in the sample, the batch is still accepted. And an operating characteristic curve illustrates a particular plan's response to a range of defectiveness. So it is a graph of likelihood of accepting a batch given an increasing proportion of defects within that batch. So again, operating characteristic curve, or OC, is a graph of likelihood of accepting a batch given an increasing proportion of defects within that batch. And selecting an appropriate sampling plan requires declaration of an acceptable quality level, or AQL, indicating what percent defective is considered reasonable. So for definition purposes, the AQL refers to the proportion of defects a consumer considers acceptable. Now, what the customer considers reasonable and what the customer will tolerate are two different issues in acceptance sampling. It is often assumed that the customer who declares the acceptable quality level will nonetheless accept up to a higher amount occasionally, recognizing the randomness in sampling and in the process. Therefore, the consumer has a second higher limit on what is usable, known as a lot tolerance percent defective. So the maximum proportion of defects that a consumer can tolerate. That is lot tolerance percent defect, LTPD, and that is again the maximum portion of defects that a consumer can tolerate. So in summary, any ongoing processes provides a background of natural variation into which troublesome assignable variation can easily blend. The highly visual tools of statistical process controls are means of making assignable variation more apparent to any observers of the process, allowing that observer to stop the production process when it appears to go out of control. The most popular of these tools is the mean chart, a control chart allowing sample means to be graphed as they become available, illustrating any changes in the central tendency of the issue being measured. Designing such a chart requires setting limits on how much variation is acceptable in production, and a task that requires a balancing the producer's risk of receiving unacceptable product because the limits are spaced too generously and assignable variation has gone undetected. Similarly, any acceptance sampling plan requires its designer to make that same choice between consumers and producers' risk when deciding how frequently to sample and how harshly to assess sample results, decisions that determine the risk of making a bad shipment for a good one or a good shipment for a bad one. And that concludes the Chapter 13 lecture. Please visit Blackboard for this chapter's expectations and deliverables, and I will see you in Chapter 14. getting close to the end, students.